time for us to talk about one of the most important topics in calculus. The topic that makes other people say, these calculus people are onto something. And that is optimization. Now, the goal of optimization is trying to get the most out of a situation. We have a procedure, our function, if you will, and there's lots of little things we could play with. Setting our knobs in the right way or pulling levers, whatnot. But in other words, we're trying to maximize or maybe minimize some particular function. Now, if you go back 100 years and people would say, look, infinite resources, we'll just, burn everything, no problem. But we know better now. We know it's like, no, there's finite resources. We really got to start striking that balance. How do we get the most out of what we have? And that's the goal for today. Optimization. Well, let's begin. So, we need to start by understanding what we mean by optimization. I like to call it the est part of calculus. Biggest, smallest, fastest. Anytime you could phrase something with an est word, that's really an optimization. Really, the idea is, or if you like the goal, make things as big as possible or as small as possible. So, some definitions. We'll say our function has a local max at a point if the function at that point is greater than or equal to the function for all points nearby. Okay, so max just says, hey, I'm bigger than or equal to. And local says nearby. And so you might wonder, well, what do you mean by near? And the answer is whatever near enough means in context, right? Sometimes near could be within 1. Sometimes near could be within 100. Sometimes it could be 0.001. You remember, the idea of calculus is you look close, very, very close. And we can keep zooming in until we're satisfied that, yes, once we've zoomed in far enough, we know what we want. So keep in mind, near just means very, very close. That's how you should think of it. Local min at a point means what? The function at that point is less than or equal to the functions that are near that point. Okay. So, in other words, it's the smallest one in terms of the output in the points nearby. Now, there's also a global, sometimes called absolute, max-min. And what does that mean? Well, it says we're a global or absolute max if the function is always greater than or equal to the function at any point. In other words, not just at, if here's my point AB, not just the points nearby, all the points, regardless of how far away you go. It's the largest one. Global min, similar idea. We're the smallest point among all possible points. Now, one thing that sometimes makes people scratch their head, and they say, wait a second, why do you insist on the greater than or equal, or less than or equal? Shouldn't it just be a strictly greater than or a strictly less than? And the answer is no. We want to have the equality signs. And so I'll briefly try to argue why. First off, we know that there are functions where you attain an absolute max multiple times. Just think of the sine function, right? That oscillates up and down. It attains a maximum value of 1 whenever you're at the peak, which of course happens infinitely often. So, if we didn't have an inequality with our global max, then we could say nothing is a global max because, look, it's not unique where it attains that maximum. So we definitely need equality for global max. But now we want to have a very simple statement, which should be, if I'm a global max, I should also be a local max. In other words, if I'm bigger than everything, I should be bigger than everything nearby. And so to have that consistency, that's why we have the equalities in our local definitions. All right, so great. We know what we're after. We're trying to find these ideal points, the points that give us our best outcome. But where do we look? Well, if we had our Calc 1 hats on, we'd say, okay, look for where the derivative is 0 or where it's undefined or at an endpoint. So we're going to put on our Calc 3 hats and we're going to say, look for where the equivalent of the derivative is undefined or 0 or at an endpoint, which means the equivalent of the derivative is the gradient. So we're going to say, look at where the gradient is 0 or the gradient is undefined or you're at a boundary point. So you might have a domain which has an edge. You say, look, it could happen on the edge. And so there you go. Now, why? Why are these the important points? Well, here's the intuition. You say, look, suppose I'm at a point on my function. So here's my domain. I pick a point. Here it is upstairs. And let's also suppose that our function, it's a reasonable function. We're going to say differentiable. And that the gradient is not 0. Well, what does that tell us? It tells us that our tangent plane is not flat, it's tilted in some way. So gradient not 0 says, look, there's some sort of a tilt. And in particular, what does that mean? Well, it means that there's a way to go up and there's a way to go down. Another way to remind ourselves is the gradient always points in the direction where the function is going up. So if our gradient is not 0, we just say move in the direction of the gradient. We're going to increase. Of course, we just say a little tiny bit, but that's okay. That's the whole idea of calculus, just a little bit. Move opposite the gradient will decrease. So if we have a gradient defined, it's not 0, and we have freedom to move, then we can't be at a max or min, because we can move and either increase or decrease the value. So there's 3 things that need to be true. So again, gradient is defined, gradient is not 0, and we have freedom to move. So therefore, we'll say, look, if any of these 3 things fail, that's going to be critical because something interesting could be happening there. So the gradient being defined, well, for it to fail, that would be the gradient is undefined. So that's one of our options. Gradient being non-zero, well, okay, if it fails, that means the gradient is 0. And the freedom to move, when we talk about that, that means that we can move around in our domain. Well, if we're at an edge, I can't move outside. So I've lost the freedom to move, which means that we're on the boundary. Now, among all of these, the one that we're probably going to spend the most amount of time on, particularly in this session, is where the gradient is equal to 0. So we're going to think about that situation. Now, suppose we found a place where the gradient is 0. Okay, by looking at the situation, solving the equations, such a place has been discovered. Ah, lucky us. The question is, what kind of point is it? Because we have this notion of things are local maxes or local mins. Of course, they might be neither. We've seen that before. So we started thinking about, okay, what are ways for us to figure out the answer to the question of what kind of point it is? And we have to be careful. It turns out that just because you're a critical point, it doesn't mean you're a max or a min. So again, you can be a critical point, but not be a local max or a local min. We've seen examples of this in Calculus 1. X cubed is an example. If you think about what does the graph of x cubed do, it goes like that, right? It goes zoom, levels off and zoom, back up. So that's what x cubed does. All right, well, let's do something a little bit fancier. So here's a surface. It's a little bit hard to see, but it's this function, 4x to the fourth minus 17x squared y squared plus 4y to the fourth. Now what's happening? Well, if you sort of trace the edge on the outside, what you'll see is it's going up and down. So it's really a very, very fancy Pringle chip in some sense. And so it oscillates between up and down. And in particular, suppose we take this and we slice it with the plane z equals 0, the xy plane. Well, parts of it will lie below, parts of it will lie above. And what's happened here is we've actually color-coded it so that the parts which lie below are shaded dark and the parts which lie above are shaded light. Now, what do you see? Well, what you see here is that if you came in along the axes, you'd be like, oh, I see here that the function is positive, goes to 0, and positive. It's positive, goes to 0, and positive. So along the axes, you say, oh, it looks like a minimum. And you can check a couple of directions. But if you shift and you come along the lines y equals x or y equals negative x, what happens? Well, it's negative, goes to 0, and then goes back to negative. Negative goes to 0, goes back to negative. So from those directions, it appears to be a local maximum. So in other words, it has different behavior in different directions. And so it's not enough just to check a couple of directions. You'd somehow have to argue from every possible direction. If you only checked 4 or 5, you might have missed a direction that has a very different behavior. The moral here is there is no first derivative test. Can't do it. Because you'd have to exhaustively check every single direction. And there's infinitely many of them. So unless you have a very nice function where you can make some kind of an argument, there's really not a reasonable first derivative test. So it's kind of disappointing because the first derivative test is in some cases the best, right? It was even more powerful than the second derivative test in some ways. And so you might say, okay, well, if there's no first derivative test, all right, does that mean there's nothing we can do? Well, there's still hope. Because remember, we had the second derivative test. Okay, maybe that can generalize. So let's think about how we get our hands on that. So the key is to understand what's happening. Now, this builds off of the idea that we talked about in a session when we dealt with Taylor polynomials. So if you haven't seen that, make sure you go take a look at that. But what we have is that, look, if we're at a critical point, the variety where the gradient equals 0. So we're only going to care about the places where we can take lots of derivatives. The derivative is undefined, forget it. We're not even going to talk about it because we can't talk about a second derivative test if we can't even take a second derivative. So at a place where our gradient equals 0, which means we have a flat tangent plane, it turns out that locally we have that our function looks like this. The height of the function at that point plus sort of a extra term here. And this extra term is based off of the second derivatives. So in other words, when the first derivatives are 0, the local behavior is being driven by the second derivatives. So by understanding what the second derivatives say, then we can get an idea for what the local behavior is. And in particular, we can answer the question, is this a local max or a local min? Great. Okay. So how do we do that without going crazy? Well, as a quick refresher, it turns out that if you have a nice little 2 by 2 matrix, and this is a nice little 2 by 2 matrix, that there are two numbers called eigenvalues, and we use the symbol for lambda, lambda 1, lambda 2, where if you take this quantity, a times c minus b times b, then that's the same as taking lambda 1 times lambda 2. Now, if they're both positive, what that's saying is that in any direction, you're going to be going up. But really, the picture is both positive, our local behavior is going to be like a bowl. So there's our function, and then locally we're going to drift up. Everything's positive. If we're both negative, well, then that says what? Locally, our function is doing something that looks like this. So it looks like an upside down bowl. So being both negative is going to tell us we're at a local maximum. Now, if one of them is positive and one of them is negative, in other words, they have different signs, well, what does that mean? Well, it means in some directions, it's going to feel like you're at a local max, But in another direction, it's going to feel like you're at a local min. And in terms of the picture, what you get is you get what we call a saddle shape. So if you think about like a saddle on a horse, in one direction it has this shape, but in another direction it has that shape. So min in one way, max in another way. And therefore we say, look, it's a saddle. A saddle means it's definitively not a local max or a local min. Now, what if one of them is 0? Well, the answer is the second derivatives are not really enough to determine the local behaviors. You'd have to push further back into either higher order derivatives or do some other exploration of the function. For our purposes, if we do have one of them as 0, we're just going to say indeterminate. We don't know. In other words, we're just going to say we'll stop there and just be satisfied with having one of life's little mysteries. Okay, with this in place, we're now ready to say what is the second derivative test. And remember, the key here is to go off of this matrix and look at this quantity. So in particular, fxx times fyy and minus fxy squared, because fyx and fxy will be the same. All right, so here we go. If we're at a critical point where our gradient is equal to 0, then we compute this value d. And it should look familiar. fxx times fyy minus fxy squared. In other words, it's that determinant of that 2 by 2 matrix. Okay, cool. And as a reminder, even though we just talked about it 2 minutes ago, this is, again, the multiplying those two numbers together. So here's the thing, is we don't care about the value. We care about the sign. We saw the sign, and it opened up our minds. We saw the sign. So remember that. Focus on the sign. And so we want to make sure we figure out the sign. Now, what can happen? Well, one thing that can happen is, what if our sign were negative? The only way we could get a negative by multiplying two numbers together is if one were positive and one were negative. And so if the result of this value is negative, then it says you're at a saddle, all right? Because you have one direction you think you're a min, and the other direction you think you're a max. So if the value is negative at a critical point, remember, this is only for critical points. Any other points need not apply. So it's only at critical points. Okay. So negative means saddle. Good. Good. Now, what if it's positive? Well, here's where things get interesting, because they could both be positive or they could both be negative. If they were both positive, local min. If they're both negative, local max. So we have to have a way to sort of break the tie. So what we're going to do is going to push a little bit further. And the way we do that is we say, okay, if the result is positive, so in other words, this d expression is positive, now look at fxx. Okay, and do what? Well, if xxx is positive, then it's a local min. And if xxx is negative, it's a local max. Now, what's going on there? Well, the idea is actually really beautiful and simple. And it boils down to saying, look in the slice. So what do we mean by that? We say, okay, if I'm at a point which is either a min or a max, if I slice, then I'm still going to be at a point where in the slice I'm at a min or a max. So maybe my shape is doing this, and now I come through, we do a slice, and we say, okay, let's fix y. So we fix y, and when we slice, lo and behold, we see this shape in our slice. We say, okay, now what do we want to do? Well, we want to figure out, is that a min or a max? And we can go back and use our old tools. And in particular, we still have the second derivative test from single variable calculus. So as a reminder, what does that say? Well, it says if your second derivative is positive, then your curve does something like that. And if your second derivative is negative, well, your curve is something like this. And of course, if your second derivative is 0, we have no idea what's going on. All right, so what happens is we look in the slice, the second derivative with respect to x, using the second derivative test from single variable calculus, tells us if we're a min or max in the slice. Whatever we are in the slice, we are going to be for the function as a whole. All right, so that's our case if we have a positive value. If the result is 0, we just say, don't know, not enough information, thank you, and move on. Inconclusive. So there we go. Now, on a side note, it says it right here on the bottom. I just want to emphasize it. Some people might say, why are we treating fxx special? Why not fyy? And the answer is absolutely, you can use fyy. It doesn't matter. If fxx is positive, so will fyy be positive. If fxx is negative, so will fyy be negative if you're in this scenario where d is positive. So use whichever one is convenient. It doesn't matter. But you have to pick one and you have to follow the rules. So it's actually not so bad. Once you understand, how the test runs, it says, oh, okay, I'm just going to look at this little product here of fxx fyy minus fxy squared. That's telling me about two numbers multiplied together. And I'm just trying to figure out whether those two numbers are both positive, both negative, or different sign. And just figuring out how that works and put it all together. And life is good. The actual test is not the hard part. The second partials test is usually the easy part. So what's the hard part about these problems? And I will tell you that probably the hard part about these problems is figuring out where the gradient equals 0. Remember, we can't apply the second partials test until we figure out where the gradient equals 0. Now, I'm going to give you some advice because, we're friends. I want you to have this wonderful knowledge. Okay, so how do you solve gradient equals 0? Well, what happens is when you have the gradient of your function equals 0, that leads to two equations and two unknowns. Now the problem is these equations are not going to be friendly. In some cases, they're going to be messy. Usually, we'll mainly do this with polynomials. So how do you solve two equations and two unknowns? Generally speaking, you have two main tools, and I want you to be aware of both of your main tools and to be on the lookout for them. Your two main tools are substitution, which says, look, I can solve for one of the equations. I can get a variable by itself. Once I can do that, put it into the other equation, and I get down to one equation, one variable. And the other thing to be on the lookout for is factoring. And in particular, you want to have factoring things equaling 0. If you can get there, beautiful. You've made fantastic progress. Because if you have a bunch of stuff that multiplies, and it multiplies to 0, that says, oh, one of the individual pieces has to be 0, and that dramatically narrows down your search. And you can make wonderful, wonderful progress. And that's it. As long as you can use those two tools, you'll pretty much be able to solve almost all the problems that we're going to ask you. And of course, it just takes practice, and which means time to go do some practice. And once you get the hang of it, you'll be great. All right, thanks for coming. Hope to see you again soon.